In section 4.6, we work with a type of problem called optimization problem. And basically, we learned in sections 4.2 and 4.3 about finding critical numbers and whether those might be maxes or mins and how to find inflection points. So we're going to use those ideas to solve this class of problems. Now, what I've pasted from your textbook are steps for solving these types of problems, and I'll let you read through those for yourself. And I also mentioned you might want to watch the video that's in the e-text for this section, and if you could work through as many of the examples in the section as you can, that would be helpful. I'm going to go through a few of the exercises from the end of the section, and the first one is number 14. So there is a rectangular storage container with an open top, and it's supposed to have a volume of 10 cubic meters. The length of the base is twice the width. The material for the base is $10 per square meter, and material for the sides is $6 per square meter, and we want to find the cost of materials for the cheapest such container. So again, with optimization problems, we're usually trying to maximize or minimize something. In this case, we want to minimize cost, so it's important to recognize which quantity you're trying to maximize or minimize, because then you need an equation for that quantity or a function. So next thing is I would try to draw a picture. Now, you know I'm not the world's greatest drawer, but I learned when I was young to draw a rectangular box, so I'm not so terrible at that. And for now, until I kind of figure out everything that the question is telling me, I'm just going to label the dimensions x, y, and z. Now we're told that there's no top on this, but there is a bottom, which is not really visible in the picture. And the volume is supposed to be 10 cubic meters. And it says the length of the base is twice the width. So I'm going to say the width is y. And so the length of the base, which I would say is z, is twice the width. So I'm going to relabel my diagram with that dimension that I'm calling the length of the base to be 2 times the width value of y. So in general, for a container of this shape, the volume is length times width times height. And in this case, the length is what I'm calling 2y, and the width is what I'm calling y, and the height is x. So that is 2xy squared. Now that's supposed to equal 10. This, by the way, is what we call a constraint equation, just for a little bit of trivia there. And so one of the steps in the steps for problem solving on the first page has to do with being able to potentially solve for one variable in terms of another when you have a function in more than one variable. So we'll come back to that. Now again, we need a function for cost. So the cost, and maybe I should call this total cost, is the cost of the base plus the cost of the sides, and the top is open, so there's no cost to the top. So the base has dimensions y by 2y, and that costs $10 per square meter. So the area of the base is 2y squared square meters, and it's $10 per square meter. So 2y squared times 10 is going to get us the cost of the base. Now the sides, I have two sides, the front and the back, that are x by y area, and that costs $6 per square meter. Plus I have two sides, the left and right sides, the way they're pictured, the way my drawing is, and those are x by 2y. That's not a decimal point, it's supposed to be a multiplication. And those also cost $6 per square meter. And again, I always, when I'm doing these, I'm double checking, I'm triple checking, so I have a front and back x by y. I got two of those at $6 per square meter. I have a left and right side of x by 2y, and I have two of those at $6 per square meter. So if I put all this together and try to do a little bit of simplifying, I have 20y squared plus 12xy plus 24xy. 2 times 2 times 6 is 24. And that is 20y squared plus 36xy. And that is the total cost. Now, the thing is that this is an equation with two variables, x and y. Okay, so what we're going to do, and this is a typical step in the process, use volume constraint. Now, we could either solve for x in terms of y, or we can solve for y in terms of x. It really doesn't matter. I think in this case it'll be a little bit easier to solve for x in terms of y, but you truly could do it either way. And just as something to try, after I get done going through this whole thing, you might try it yourself from this point on, going the other way. Try solving for y in terms of x and see if you get to the same result. You should. So the volume, which is 2xy squared, has to equal 10 cubic meters. So if I solve that for x, I get 10 over 2y squared, or 5 over y squared, or if you prefer 5y to the negative 2, that's also fine. So now I'm going to write my cost equation strictly in terms of y. That is 20y squared, right? So I'm calling this, well, let me write it down here. This is my equation for total cost, but I'm simplifying my notation and call total cost just capital C. So that's 20y squared plus 36 times x, which is 5 over y squared, times y. So my cost function, if I simplify a little bit more, the y in the numerator can cancel with one of the y's in the denominator. And 36 times 5, if you check that, you should get 180. So here is my cost equation. So I want to find a minimum on this function. So to find where c of y has a minimum, I'm going to find critical points or critical numbers. So to do that, I find where the first derivative is 0 or undefined, and the first derivative is 40y minus 180 over y squared, using the shortcut rules. So again, critical points are y values in the domain, don't forget that part, of c of y. Where c prime equals 0 or is undefined. That's the definition of critical points. Now, this derivative, c prime, is undefined when y equals 0, but that's not in the domain of capital C. And in this context, it doesn't really matter. I mean, we wouldn't be considering y equals 0 because y is one of the dimensions of the box. And if y is 0, then we have no box. So we need y strictly greater than 0. So we can safely set this function equal to 0 because we've already checked about where it's undefined, and the place where it's undefined at y equals 0 is not in the domain of the cost function. So now if I solve this for y, I get that y cubed equals 180 over 40, also known as 9/2. And so y is the cube root of 9/2. Now, you might think, okay, we're finished, but we are not finished because we have to actually test and make sure that this does in fact result in a minimum on the cost function. So you cannot just assume that this solves for the minimum. Perhaps it is a place where C has a maximum, or maybe C has neither a max nor a min here. We've had both of those situations occur. So we don't know until we test, and I will use the first derivative test, although you could also use the second derivative test if you wanted. And by the way, if it's helpful to you, you can put that into your calculator and see that the cube root of 9/2 is in the neighborhood of 1.65. So I'm using the same technique that I've been using. I need to pick a value for y to the left of the cube root of 9/2. 1 is a nice easy number to plug in. When I plug 1 in for y into C prime, make sure you're plugging into the correct function, I do indeed get a negative. And then I can pick something bigger than 1.65. And again, depending on what you have in terms of technology, for me, I'm going to pick something big like 10 because it'll actually make it easier for me to see what's going on. And when I plug y equal 10 into C prime, or if you have your calculator, you could be using, for example, y equals and the table feature. Just make sure you're looking at the correct output. Then my C prime is positive for y values bigger than cube root of 9/2. And what that tells me about my cost function is that it is decreasing and then increasing. And so this is not only a relative, but an absolute max at the cube root of 9/2. And how do I know that it's absolute? Because I can see the behavior of my function C is decreasing and then increasing. So this spot must be the lowest overall, again, in my domain of y greater than 0. There may be other parts to the function for y less than 0 that I'm not considering and that don't matter in this context, and maybe if I were considering those, I wouldn't be able to say this is an absolute max. I'd have to check into that. But right now, for the context I'm in, where y has to be positive, I can say for sure I've got an absolute maximum here. Now, the other thing when you're doing this kind of optimization problem is you want to go back to the instructions and make sure you answer the question. The question was, or the problem, find the cost of materials for the cheapest such container. So now I actually need to know the cost at the cube root of 9/2. And again, this is something that you would put into your calculator. And when you plug cube root of 9/2 into the cost function, not C prime, but the cost function, you should get 163.54 as your cheapest cost. And make sure that you actually check that for yourself. Make sure that you're getting the same result. If you're not getting that, then you should let me know so that we can figure out what the problem is.